So hello dear students. Today I am going to describe a fresh new chapter in physics, which is the first chapter, which is called Units and Measurements in class 11th. And it is a chapter that you will learn the very first whenever you embark upon the study of physics, when you start your class 11th in the schools. So units and measurement we are going to talk about in this particular video, and then later on in the next video we are going to do some problems related to this particular chapter. And so we let us start how we can understand about this particular concept. So to start with, let us say we are talking about physical world. So what is the physical world? The world that we see around us is the physical world. And whenever we are talking about the science of physics, then we are talking about physical quantities. So we need to know what are the physical quantities we are talking about and what are the relationships between different physical quantities. So you can say that whenever we are talking about physics, we should know we should have some measure of a physical quantity. So anything which can be expressed in numbers is a physical quantity. Like for example, if you have the length of a human being, either it is 6 feet or 6.1 feet or 2.7 feet or whatever, or 7 meters or whatever, the length is a physical quantity because you can express it in numbers. Similarly, the mass of a object, either it is 1 kg or 90 kg or whatever, so that again you are expressing a certain property of the material with some number which is associated with that property. So that if you can express it in numbers, then you can say that you have a physical quantity. And so any property of material or system that can be quantified by measurement would be called a physical quantity. For example, your height, your weight, the speed of a car, or the temperature that you are seeing, observing outside. So all these things are physical quantities. So you can say physical quantities are broadly classified into two different types. One is the fundamental quantity. So let us say these are the quantities which are basic in nature and independent of each other. For example, if you have mass, so mass is independent of, let us say, length. So any object's mass is independent of its length. So basically they are independent of each other and they are not related to each other. Similarly, any event that is taking place at some time, that time that at which that event is taking place is independent of the mass of that system in which that event is taking place. So all these mass, length, time are the fundamental quantities. There are other fundamental quantities also present in the physical universe. So as we will see later, there are actually 7 physical fundamental quantities which are there in nature. And then you have derived quantities. That is, you use those quantities to derive other quantities which are not fundamental in nature. For example, speed. So speed is basically distance covered by an object per unit time. So it is distance divided by time. So its unit is distance by time. So length by time is the basic unit for derived quantities. And so derived quantities are related to fundamental quantities because they are actually derived or extracted from those fundamental quantities. So basically you have two types of quantities: fundamental quantities and derived quantities. So the International System of Units, so SI units, so they have actually made a common standard for measurement across the world. So any measurement that you are doing here, let us say for mass, if you are doing some measurement for mass and you say it is 1 kg, the same object when taken to America or Russia, how will they measure it and what would be the mass of that object if they are measuring it there? So there has to be a standard. So you have to compare the mass with the standard, and that standard is basically set by you can say a world scientific organization which is called System International Units, or the SI system. So according to that, there are 7 fundamental quantities and their corresponding SI units. So a length, for example, is a fundamental quantity, and its SI or standard international unit is basically system international unit is meter, and the symbol is M. Similarly, mass has an SI unit of kilogram and symbol is kg. Time has an SI unit of second and the symbol is S. Electric current has a SI unit ampere and the symbol is A, capital A. Thermodynamic temperature, the unit is Kelvin and the symbol is capital K. Amount of substance is basically measured in terms of mole and the symbol is MOL. Similarly, luminous intensity, which is the brightness, you can say, of any particular object, it is basically measured in terms of a unit called candela, and the symbol is CD. Apart from this, there are supplementary units. So there are 2 supplementary units like the plane angle. So basically, when we're talking about angular displacement or angular position of an object, that is at what angle, like for example, you're measuring the angle of the top of the tree from the base. So you're measuring the angle which is measured in the SI units for that would be radian, and the symbol is RAD. Similarly, if you have a solid and that solid is basically having a, let us say if you have a sphere, and then the cone that the sphere that makes with the surface of the sphere for a particular surface area inside the sphere, that cone would have a solid angle which is measured by this unit, which is steradian or SR. So we will talk about the solid angle and plane angle, etc. later on, how to measure them and how to actually define those quantities. So basically you can say angle and solid angle, plane angle and solid angle are supplementary units, and basically they are not fundamental units because they can be expressed again with the help of fundamental units, but then they are called supplementary because they are used quite often in physics. So let us say all other units are derived units. For example, force is the unit of force is Newton, and it is basically the definition of force is mass times the acceleration of the object. So mass is in 1 kg and acceleration is meter per second square. So it is rate of change of velocity, and velocity is meter per second, and the rate of change of meter per second is meter per second square. Rate of change of velocity with time. So this is the unit of 1 Newton expressed in terms of fundamental units is 1 kg meter per second square. So if this is a derived unit, a Newton is a derived unit. So now when we're talking about any measurement, we talk about certain things like the accuracy, precision and errors. So whenever we are measuring, let us say we are measuring the length of an object or we are measuring the mass of an object. So we use some physical measuring device like the scale or let us say a measuring balance or something. And whenever we are using that, according to the physical constraints that are present while measurement, you have certain difference from the actual mass. Whatever you are measuring is slightly different from the actual mass or the actual quantity or the actual value of that quantity that is there. So we have to actually talk about that also in physics. So we have to talk about the accuracy of the measurement. So if I say my measuring instruments gives me 10 kg of mass, whereas the actual mass is just 1 kg, then I have a huge, usually inaccurate measurement. So we should express how accurate a measurement is. Unless we don't do that, then it is not reliable actually. So we have to have some estimate of the accuracy of the measurement. So what is accuracy, what is precision, and what are errors? So let us talk about them. So let us say if you have, let us say you are actually you are pointing an arrow towards a bullseye. Okay, so you are basically firing an arrow towards the bullseye, and then it does not strike the bullseye, and it strikes a certain place a little distant from the bullseye. So how far or how close are you from the bullseye? That is the accuracy. So it tells you how accurate your measurement is. So if you strike it straight into the bullseye, then in that case you are 100% accurate. Whereas if you are slightly deviating, so how much is the deviation from the bullseye? That measure would tell you how accurate your measurement is. So how close a measured value is from the true value, that would tell you the accuracy. Similarly, precision. So if you are making a number of measurements, so you have some length or mass or something you are measuring, and then you don't know actually if the measurement is accurate. So you measure it number of times, and each time you see your measurement is how close it is to the previous measurement. So all the measurements, how close are they to each other? So if you make 10 measurements, how close those 10 measurements are to each other, so that would tell you how precise your measurement is. So let us say if you have again you're firing a shot to the bullseye, and you are firing a number of shots. So how those shots are clustered towards the bullseye? Are they spread far apart, or are they just clustered around the bullseye? That would tell you the precision of your measurement. And error is the difference between the measured value and the true value. So if the true value is 10.1 kg and your measured value is 10.2 kg, then the error would be 0.1 kg, which is 10.2 minus 10.1. So that much would be the difference or the error. Okay. So though when we are measuring, we have different types of errors are there, and according to when we are working in lab, so in the lab you can say there are two types of errors when we are talking about some measurement. One is called the systematic error, and the other one is called the random error. So what are systematic errors? So basically when we are talking about, let us say we are measuring the length of an object. Okay. And then what happens is when you're measuring the length, your scale is not calibrated. So actually the 1 centimeter of your scale is actually 1.1 centimeter. So whenever you're measuring 1 centimeter, you are actually measuring 1.1 centimeter. So there is an error in the actual reading, actual value, and the thing that you're measuring of 0.1. So that is a systematic error. Whatever you do in how many measurements you make, that error will remain. That would be plus 1.1 per centimeter, plus 0.1 centimeter, 0.1 centimeter extra would always be measured whenever you are doing any measurements to measure that length using that scale. So similarly, if you have a faulty balance, which measures actually 10.1 kg, whereas the actual mass would be 10 kg, the weight of the weight is marked 10 kg, but its actual weight is 10.1 kg, and you are using that weight to compare it with another unknown weight, then in that case every measurement will have a 0.1 kg of error. So these are systematic errors. They will always remain if you use that faulty system. So then also sometimes you have a personal bias. So you are measuring something but you always measure it a little higher because of the angle at which you are looking at that particular measurement, or you are measuring it with an instrument and you have your personal bias against that measurement. So that systematic error would always be there, and it will remain in all the measurements. So basically, they can be minimized by improving the experimental conditions and the techniques, and better equipments, and proper measurement techniques have to be used to get rid of these systematic errors. Then you have the random errors. These occur irregularly, and these are the random errors because the nature itself is random. The random forces which are acting around whenever we are measuring. Like for example, we are measuring the temperature of an object, but the temperature of an object is dependent upon the temperature of the surrounding, and the surrounding temperature is fluctuating with time. So these are random errors. Those fluctuations are random. Sometimes you have an increased value of temperature, sometimes you have a decreased value of temperature, and because of that random nature, you are getting some random errors, either positive or negative, and they would remain there. Or for example, you are measuring the counts in a nuclear decay, and sometimes the nucleus decays fast and sometimes it decays slower, and even actually when you're measuring the measuring instrument, sometimes because of voltage fluctuations or some other fluctuation, it sometimes measure a little higher, sometimes measure a little lower. So because of those fluctuations, you are having those random errors, and how to fix them is you have to take multiple readings and take the average. So basically, your true value would be the average, because you are taking multiple readings and each reading is randomly fluctuating over a mean, over a center. So in that case, some values are higher, some values are low. So you take the mean of all the values so that you actually get the mean. When you take the mean, and then that mean that you take or the average that you take, you can say is the best estimate of the actual value of the physical quantity that you are measuring. So let us say we are calculating errors. So the mean, what is the mean? So mean is the best estimate of a true value, a mean. So you're taking, let us say you're taking multiple readings of a length, and those multiple readings are labeled as A1, A2, A3, A4 and AN, up to AN. Then the mean value or the best estimate would be A1 plus A2 plus A3 plus so on up to AN. So you add all the values, and then what you do is you divide it by the number of measurements. So if you have taken n measurements, so you sum up all the measurements and you divide it by the number of measurements, then you get the mean or the best estimate. Then what about absolute error? That is the magnitude of error in each measurement. So for example, if the error in the first measurement, delta A1, is the error in the first measurement, it is A mean minus A1. So whatever mean you get, you subtract A1 from it, take the modulus. To take it positive, take just the positive value. Whether A1 is greater than A mean or if A1 is less than A mean, that is not considered. You just take the modulus, so you must subtract A mean by A1 and then you take the modulus. Then you get the error in the reading of A1. Similarly, delta A2 is the error in the reading, in the second reading, and that is mod of A mean minus A2 and so on. And then you take the mean absolute error. So you have all those errors and then you add them up and then you divide it by the number of observations, you get the mean in the error. So that is the best estimate of the error. So you have the best estimate of the true physical quantity, what is the value of that physical quantity, and also what is the error, the best estimate of the error in that measurements, the set of measurements that you have actually performed. Then you have the relative error, which is delta of A, which is delta A mean, which is the actually mean absolute error divided by the A mean, which is the mean value or the best estimate of the true value. So you divide the two, so you get the relative error. So let us say if you are measuring what you call 10 kgs of object has whose mass is 10 kg, and the error in that is 0.1 kg, then the relative error would be 0.1 by 10, which is equal to 0.01. So, and when you multiply that relative error by 100, you get the percentage error. So it tells you what percentage error is. So basically, like for example, you are measuring 1.1 error, 0.1 error in 10 kgs, then the percentage error would be 0.1 divided by 10 into 100. So what it will be actually 0.1 into 10, which will be equal to 1. So there is a 1% of error. So that is how you calculate the percentage error. And that percentage error is basically you are actually using it for conveniently for all the scales of measurement. Like if you measure 10 k instead of 10 kgs, if you measure 100 kgs and the error is 1 kg, then again the percentage error is 1%. So that error in 100 kg is the error of 1 kg is equivalent to an error of 0.1 kg in 10 kg measurement. And so that percentage error basically tells you it is independent of the scale of measurement. So it is independent of the scale of measurement. It just gives you some idea or estimate how much the error is compared to the actual value of the measurement. So let us now talk about the significant figures. So that is also a very important thing. So let us say if you make a measurement and the measurement is made and it is expressed in certain numbers, then the number of digits that are reliable in that measurement would tell you that something about the quantity, and they will tell you the precision of the measurement. So if we talk about significant figures in any measurement, like for example, if you have a measurement that is 123.45, so that measurement has 5 significant digits. Similarly, 5007 has 4 significant digits. But if you have leading zeros, 0.0045, so that some zeros are in front of your measured value. Like for example, you can express it in numbers, and in that case it is 0.0045. Then 4, 5 are the 2 significant digits, which are 2. The number of significant digits is 2 basically, which is 4 and 5. The rest of the zeros which are leading are not considered as significant figures, because simply because these are the two relevant things that would be changing. So in a measurement, the measurement, if it is 0.0045, then it can be the 0.646 or 0047 or 0.0043 or whatever. So the change in the readings would be in these quantities, and 00 will remain the same. That would not change. So actual changes are taking place in these two quantities whenever you are measuring. So these are the significant figures. Similarly, trailing zeros, like for example, if you have a trailing zero 35.00, then if you introduce a decimal place, then in that case 35.00 has 4 significant figures, and 35 only will have only 2 significant figures. Similarly, 3500 has 2 significant figures, but if 3500, okay, after that if you place a decimal, then in that case 3500 will have 4 significant figures. If you place a decimal after 3500, then in that case you are saying that you have accurately measured that quantity up to 4 decimal places before the decimal point. So in that case it has got 4 decimal or 4 significant figures. Now, whenever we are calculating something, like for example, we are calculating using a calculation to calculate some quantity from the measured quantities. Like if you measure mass and you measure acceleration, then you multiply the two quantities to find out what the force on that object is. So in that case, you're multiplying, then the final result should have the same number of significant figures as the original numbers with least number of significant figures. Like for example, the mass has 2 significant figures and the acceleration has 4 significant figures. So when you multiply them and express your result for the force, then the force should have only 2 significant figures, because the mass has got the least number of significant figures. But when you're talking about addition and subtraction, the final result should have the same number of decimal places as the original number with the least number of decimal places. So now we talk about the dimensional analysis. So what is dimensional analysis? It's a powerful technique that is basically to check the equations and derived relationships. So derived expression and relationships, if they are there in physical world, then you can check the accuracy or the correctness of those physical relationships using the dimensional analysis. So dimensions, basically what are dimensions? So let us first of all understand what are dimensions. So basically, like for example, we're talking about fundamental units like mass, length and time. And then we are basically talking about some physical quantity which is related, which has got mass, length and time in it. Then we can talk about the dimension of that physical quantity in terms of these fundamental dimensions. And let us say the dimension of mass is expressed in a square bracket with a capital M. Dimension of length is expressed as a square bracket L in a square bracket, and dimension of time as capital T in a square bracket. Now, for example, let us say if you are talking about velocity. Simple example we are taking. So velocity is length divided by time. So basically it is the displacement divided by time. So you can say dimensional formula or the dimensional expression for that would be the square bracket L divided by square bracket T. And so you can express it in terms of three fundamental quantities: mass, length, and time. So mass has got a power 0, length has got a power 1, and time has got a power -1. So this is the dimensional formula with square bracket inside m raised to power 0, l raised to power 1, and t raised to power -1. So similarly, if we talk about force, the force is mass into acceleration. So it is mass into velocity divided by time. And velocity again is L divided by time. So basically the dimensional formula is m into L raised t raised to power -1 divided by t. So you combine it together and you express it. So it is m raised to power 1, L raised to power 1, and t raised to power -2. So this is the dimensional formula of force. So similarly, you can have for every physical quantity, you have a dimensional formula. Now, if you have that dimensional formula for every quantity, then you can do some things like checking the validity of an equation, and you can also guess the form of an equation. You can even guess what the equation would look like. For example, let us start with the first thing. Let us check the correctness of the equation, and that is called the principle of homogeneity. That is, there is some equation which has got a left hand side and the right hand side, then the dimension of the left hand side should be equal to the dimension of the right hand side. So let us say if you have an equation like v is equal to u plus at. So the dimension of v is L t raised to power -1, and the dimension on the RHS, that is u plus at, is u again is velocity, which is L into t raised to power -1 plus a times t, where a is L into t raised to power -2 times t. So that gives us L t raised to power -1 plus L t raised to power -1. So basically in the RHS, again, the dimension is Lt raised to power -1 plus Lt raised to power -1. So you can actually add two physical quantities which have got the same dimensions. You cannot add two physical quantities with different dimensions. So here again, U and At have the same physical dimension, and also the LHS also has the same physical dimension. So this equation is correct. Similarly, if you want to change the units, like if you have one unit like kg, u1 is kg and u2 is let us say gram, then the quantity n1 which is expressed in kg and the quantity n2 which is expressed in grams, there is a relation between the two. The same quantity when expressed in kg and then expressed in grams, then what is the relation? What is n2, let us say, with respect to n1? So if it is 1 kg times 1 kg times how much would it be in terms of grams? So let us say, let me just show you. So we have this equation here. So you have here N1 U1 is equal to N2 U2. Okay? So U1 is kg and N1 is, let us say, 10. So it is 10 kg. So 10 kg. And then you have N2, you have to express it in grams. So N2 grams. Now you know that 10 kg, 1 kg is equal to how many grams? It is equal to 1000 grams. So you can say 10 kg is equal to N2 times grams. So you can actually write kg in terms of grams here. So you can write 10 into 1000 grams is equal to N2 grams. So then N2 would be nothing but 10 into 1000 divided by 1 gram. Okay, so that would give us 10,000 grams. So basically it would mean that 10 kg is nothing but equal to 10,000 grams. So this is how you can, to convert units. Again, it is helpful if you know the conversion relationship between the two units. So if you know the conversion relationship between kg and grams, then you can easily, using this basic principle, N1U1 is equal to N2U2, you can convert from one system of units to the other system of units. Similarly, if you are talking about relationship between physical quantities, then let us say if you are finding the time period t of a simple pendulum, which may depend on its mass, length and gravity. Let us say you know something about the system and you say that the time period of a pendulum will depend upon the mass of the bob of the pendulum, length of the pendulum and the gravity, the acceleration due to gravity, g. Then let us assume T is basically m raised to power a, m raised to power a, l raised to power b, and g raised to power c. So basically T is m raised to power a, l raised to power b, and g raised to power c. Then you can, you don't know what a, b, and c are, but you know there is a relationship between time and these quantities, m, g, and l. So how do you find the values of m of a, b, and c? That is the basic thing that you require. So you basically, what you do is, it is very simple. So what you have here, you can say, write the dimensional formula of time, that is T here, and then you write the dimensional formula of mass. So this is equal to m raised to power a. Then you have the dimensional formula of length, which is L raised to power b. And then you have the dimensional formula of the acceleration due to gravity, which is distance by time square. So it is L raised to power c and time raised to power minus 2c. Okay, so you see time here on the left hand side is raised to the power 1, and what about the other quantities? M is raised to power a on the right hand side, but there is no a on the left hand side, so a has to be 0. Similarly, L has got two powers, L raised to power b and L raised to power c. So you can say you can say b plus c is equal to 0, because on the left hand side you don't have any L. And what about t? You have t raised to power 1 on the left hand side and t is equal, raised to power minus 2c on the right hand side. So c basically is equal to minus 2c is basically equal to 1. So you have these three equations. You have equation number 1, 2, and 3, and you have three unknowns. So from there you can calculate the value of a, b, and c. So a is equal to 0. Similarly, from the third equation, c is equal to minus half, and then b plus c is equal to 0. So b is equal to plus half. So what you get is B is equal to plus half and C is equal to minus half. Okay, so you just plug in these things, so you get T here. So T becomes proportional to, let us say m is 0, so it is proportional to m raised to power 0, a is 0, so m raised to power 0, then L is B, so L has got a power of B, so B is equal to plus half, so L is raised to power plus half, and G raised to power C, and C is minus half, so G raised to power minus half. So which gives us, it is proportional to under root of L by G. So finally you get the formula for T, which is some constant times under root of L by G. So this is how you can actually guess the relationship. Okay, so you can actually guess the relationship if you know, you have done an experiment and you know what would be the parameters or quantities on which your measurement would depend. Then you can actually, after your measurements, you can actually find out what would be the kind of relationship between the different physical quantities. So let us now sum up everything. These are the key takeaways in summary. Physics is built on measurement of physical quantities. The SI system provides a standard of 7 fundamental units. A set of 7 fundamental units is based upon the SI system, and then every measurement has got some error. We can analyze those errors to understand the reliability of the result that we have. Then we talked about significant figures, and what is significant figures actually tell you what the precision of your measurement is. And then you can use dimensional analysis as a versatile tool for checking equations and deriving formulas.